Okay, I'm Jim Rayfield. I'm going to be talking about blockchain today. I'm from IBM Research. This is my old department from last week. This was Internet of Things, AI, and blockchain. Now it's called cognitive manufacturing, whatever that is. So I got my Ph.D. from Brown in '88. Geez, that's a long time ago. I've worked at Watson since '89. I started in fault-tolerant hardware development and moved to object transaction processing software. And the country company's first-of-a-kind project where I met Professor Lev.
All he knows about there's an insurance company somewhere in the
yeah. And we did EGBs for a while, but they never took off. We did relational blocks. Each one of these is actually a lecture in itself. We did data power XC10 microcode, mobile healthcare web services orchestration, which we got a paper out of and a patent. And last year we did a blockchain app for an animal testing company. So I'll talk about that briefly. And this year I'm doing homomorphic encryption. You have to look that up. So these are some of the papers we wrote together. This one, we invented Web 2.0. This got 501 citations. For Aetna, who didn't want it. I'm bitter. This was my PhD thesis, basically, with my advisor, Harvey Silverman. Built a multiprocessor and programmed it.
So Harvey speaks Yiddish, is that true?
Certain forms of Yiddish. I think it's the reform. Let's see. This was one of the first projects that we actually, I thought was a good deal. Long-running business processes. We came up with a system for doing that. This is Web 2.0 again. Edge servers, and yeah, good stuff. And the bottom was this WebRB's relational blocks. And apparently I have 25 patents issued. The system at IBM is you come up with an idea and you try to write a paper and they say, have you patented yet? And you say no, and they say, go patent it and come back. We'll approve the paper then. So every paper we wrote has a patent behind it. What was that? Or two. Yeah, some of them got split into multiple patents. So this is the outline of my talk today. So I'm going to say what blockchain is. Give you an example of card processing that could be done with blockchain. You'll talk about when blockchain is useful. We use Hyperledger Fabric. I'll point out Hyperledger is a trademark of the Linux Foundation. I'm required to put that in the talk. And I'll talk about digital signatures and a little bit about Bitcoin because the origin of blockchain is really Bitcoin. Even though not exactly, but I'll talk about that. And then I'll touch on Ethereum. What is blockchain? Blockchain is a distributed, replicated database. Replicated across all the peers. The peers are the instances that run blockchain. It's an append-only database, so you can only add new blocks to it. The blocks are immutable after commit. So each block has the hash of the previous block. So if you change any block in the sequence, they don't match the hash anymore. So you can always tell, because the whole blockchain is basically public to any participant. And appending the database requires approval of all the peers. That's actually configurable, but you can just pretend for the moment it requires all the peers to approve it. Okay, so this is credit card processing. So this is what happens behind the scenes when you buy something with a credit card. You the person swipes the credit card through the machine, and the machine says bing, and your credit card is approved. But behind the scenes, the first thing they do is send it to the merchant's bank, and the merchant's bank then sends it to the credit card company, and the credit card company then sends it to the bank that issued your card, and they think about it for a while, and they say, oh, okay, and it all goes back to the credit card machine, and it says, authorized. Afterwards, there's two things that have to happen. There's clearing and settlement. Clearing, you have the final transaction information is sent from the merchant bank to the issuing bank for posting on your credit card statement. You have fees and charges calculated. You have currency conversion if it's necessary. And then in settlement, you have to calculate the final amounts and transfer it through the Federal Reserve System. And this happens, typically in the next business day or maybe in 2 days. So the clearing goes to the merchant bank, the Visa, to the card issuing bank. The card issuing bank generates eventually a statement, and then you have to pay them eventually. And the card issuing bank sends the money to the Visa settlement bank, and the Visa settlement bank sends it to the merchant bank, and the merchant bank credits it to the merchant account. All this is behind the scenes. So let's see what's wrong with this. This is, it shouldn't really take this long, right? This is basically a legacy of paper processing. There's a couple of days of float out there, which somebody's benefiting from, probably not the user. All the interactions are pairwise. So the merchant has an agreement with the bank has an agreement with Visa, and 1 business days or 2 is required for the settlement. Also, there's multiple databases because each entity keeps its own database. This could be replaced by a single database with blockchain, providing instantaneous settlement of your credit card purchase, well, almost. And in theory, less friction and less cost for the credit card processing.
So Jim, you're arguing that the reason why it takes so long is because of the multiple databases?
Well, the Federal Reserve database only runs overnight because it's still running on batch.
So is that the reason? Because we're arguing that second letter is because of the float. They could get away with the float issue because they can say, listen, multiple databases, what are we going to do?
Yeah.
Okay. So that's the real issue. Okay.
Well, part of it. The rest of it is all the complexity. So blockchain is useful when you don't have a trusted central authority to maintain the database, as we don't have in this example. If you have a trusted central authority, like the Federal Reserve for banking, you don't need any blockchain. You trust them, and they do the transfers. They do automatic clearinghouse transfers every night, funds transfers. So blockchain is useful for multi-party distributed databases without a central trusted authority. So this is specific to Hyperledger Fabric. So blockchain is, as I said, is a distributed transaction ledger. It's append-only, immutable after commit. Besides the ledger, there's the world state, which is it's really a cache of all the transactions that have been run in the past. So you could actually recompute it, just run the transactions again. But usually they keep it in the database for efficiency. It's kept synchronized by consensus via the ordering service, which I'll talk about a little bit. And each block in the chain contains the hash of the previous block, which contains the hash of the previous block, back to the genesis block, I think they call it. And so if you modify anything in the database, it's immediately apparent to anybody that can read it, and anybody that's participating can read it. Okay, so Access is based on smart contracts, which are actually called chain code in Hyperledger Fabric. So they're basically, the chain code is read-write and read-only functions. Currently in JavaScript or Go. I think they have Java too. Yeah. So all the accesses are done via the chain code. So if you have a query, you call one of the read-only functions, and if you have a write, you call the rewrite function. So the ledger is the record, all the rewrite function calls and their parameters. And the world state is a database that comes from running all the transactions in the ledger at the current moment. Oops. So this is literally what the blockchain log looks like. You know, create account 1234, deposit 1234, $42, get balance of 1234, create account, transfer $50 from 1234 to 5678, which typically fails because 1234 only has $42. Buy shopping cart is a more complicated function. Basically, you have to pass the stringified serialized shopping cart contents.
So is this code visible to all the participants also?
All the peers.
They can see, so they can see the code.
Yeah.
Do they actually bother to read it?
We'll see. Okay. So each peer hosts a ledger copy, the smart contracts, which is the same as chain code, and the world state database. Usually you have one peer per organization. So in the credit card example, the merchant would have a peer, the bank would have a peer, a Visa would have a peer, and so forth. For read-only transactions, you can query the local world state of any peer. That's the question of which one do you choose, because they're not necessarily synchronized. That's a good question. For read-write transactions are a bit more complicated. So this is the block diagram from the Hyperledger Fabric website of the blockchain peer. So A is the application, P is the peer, S1 is the chain code server. The chain code runs in a separate server from a separate address space from the peer. The ledger is run in a separate address space also, and the order is down here. So the first step is you connect to the peer, and then you say, I want to call this function rewrite function or read-only function, and you pass the name and the parameters. The parameters are always strings because it's the only thing you can pass between address spaces of different types. So let's see. Okay, so when the peer gets the proposal, the peer passes along to the chain code server, and the chain code server generates a query or update against the ledger and sends it back to the application. And then, so if it's a read-write transaction, the application then sends the request to the order, and I'll have to explain what that is. And if the order approves of everything, they get sent to the peers to be executed against the ledger. Okay. So once again, the client initiates the transaction. So the transaction has to be sent to enough peers so that if they all approve it, it can be committed, which you can assume is basically all of them for now. Although you fiddle with that. the peers verify, this transaction proposal is well formed. It's not a replay of a previous transaction. The signature is valid. The client has permission to write to this channel. And then the peers, called the chain code server, to execute the chain code against the current world state. So it produces a response value and a read set and a write set for the database, the world state database. So the read set is just whatever you read, and the write set is whatever you modified. But there's no world state updates at this point, right? The chain code is basically running against the read-only copy of the world state. So one of the catches here is you can't see what you've written in the chain code. So if you write 42 in a location in the world state and you read it back, it'll say, well, it'll say whatever the previous value was, because this is just a simulation at this point. So, the application client, which is basically the SDK that comes with Hyperledger, broadcasts the proposal in response to the ordering service, and the transaction proposal and response is delivered to all peers on the channel. And the peers sign that they approve the transaction, and they check that enough other peers have approved the transaction to let it through. And then the peers all verify the read sets are current, unchanged, and they also check the write sets don't conflict with any other transaction on that block. Okay, and then each peer appends the block to the channel ledger and writes the write set into the world state. So the read set and the write set are produced by the trial run of the chain code, and when they commit to the world state, they don't run the chain code again. Yes?
What's a block?
In Hyperledger, it's basically 1 second worth of transactions. But it's all configurable. Basically, the order listens until it times out, typically like 1 second, be a typical timeout, and says, well, whatever transactions I've heard in that time, I'll put them together in a block and commit them together in a block.
So what if there's like 2 requests for some amount of money that conflict?
Yeah, then that's the purpose of the order is to decide the order of the transactions. And the second one will fail, but it still gets written to the ledger. It just gets written as invalid transaction. Okay, so the chain codes are not re-executed, and there's an event emitted, but that's not interesting.
When you talk about the peers verifying and then the peers executing the chain code, does that happen synchronously or asynchronously? I mean, do all the peers have to agree to verify the code before any of them execute it, or are they all, running to completion on their own?
Well, they all run asynchronously the simulation of the chain code, and then they all reply with their, acknowledgement and signature saying it's okay. And then the order collects them all and passes them back, and they get checked to make sure they have enough approvals. And if they have enough approvals, they get executed for real at that time. That's your question?
Yeah.
Okay. Yes?
If enough clients use connection to the others, will that crash the whole system?
It depends. I guess it could, but the order is supposedly designed so that doesn't happen that often. I'll talk about the order next, I think.
If they come up with a new protocol, or this is basically two-phase commit, the way you're describing it, when you strip off all the blockchain goop,
It's Raft.
so You're not gonna tell me, or?
Raft.
Okay.
Raft algorithm.
Sorry, I asked.
Yes. So there's sorry.
Sorry, are peers just a third party whose job it is to execute change?
They're in the sense that they're not running an application. They're a third party in that sense. But you have to basically decide which peers you want to have talking to each other. So when you set up a blockchain, a Hyperledger system, you say there's going to be 3 peers and they're owned by these 3 corporations, and they all agree to talk to this order and receive requests from these applications. So you can add peers to a running system, but it's tricky. I've done it, but I wouldn't want to do it again. Answer your question? Okay. Yeah. So Leslie and Lamport came up with this system called Paxos a long time ago. And nobody's been able to understand it ever since then. So this guy is a famous guy, John Osterhout at Stanford University. He was also at Berkeley, and he also worked at Sun, and he couldn't understand it. So this is a quote from his paper on a raft. So basically, he came up with this raft algorithm for consensus achievement in a dynamic system. So a raft elects a distinguished leader, and the leader has complete responsibility for ordering the different events. Basically, the leader writes a log that he receives from the clients and replicates them to other servers and tells the server when it's safe to apply log entries. And Raft is not that understandable either. There's a simulation here if you want to go there, but yeah.
Better than Paxos, though.
Better than Paxos. Yeah, this is tiny.
You still teach Paxos, right?
And Raft, yeah.
You find Paxos difficult to explain?
Yes.
Yeah. I haven't even looked at it because everybody said it was too hard. So,
Let's say I attempt to explain it.
okay,
Which
good
is
enough.
data over me attempting to understand it.
Yes. So Raft basically, each peerish thing starts as the follower, and if he doesn't hear from another leader, he progresses to the candidate state, and if he gets a majority of votes from the other servers, he becomes the leader. If not, you can somebody else becomes the leader. Or there's a new term declared, and these are some of the Raft axioms. It goes on for pages like that. Okay, so blockchain relies very, very heavily on digital signatures, which you can use to authenticate the author of a message. And digital signature algorithms consist of a key generation algorithm, a signing algorithm, and a signature verifying algorithm. So this is a digital private key. I created it with OpenSSL. This the key in hex. This is the private key. This is the public key. And from the public key, you can create a certificate. So the certificate has a lot of junk on it. This says, who owns it, and so forth. And it has a signature. So Hyperledger uses elliptic curve digital signature algorithm, which is it's complicated. I tried to read it, and my head spun right around. It's basically based on group theory. So
So is this the homo?
no, that's even worse.
Let's back. So what is it doing? Can you just walk us through the steps here?
No.
You coded it up for the small computer. Right?
Sorry?
You coded it up for the small computer. Right?
I called the library.
Okay.
Yeah.
So it's a quota lifted because your head's hit.
Yes, right. Yeah, it's based on prime numbers and group theory and group operations. And the elliptic curve is something you specify with like x squared equals y squared minus something or other. And it's really complicated. And this is basically you hash whatever the input is. So hello world, I ran through the hash algorithm, and you sign it with a key, and you get this big long hex string. This is like 256 bits plus a few funny characters. And the only thing you can do, you can verify the signature as verified or not verified, and that's it. You can't do anything else with it because it's yeah. The first time I tried using signatures, I was trying to work backwards from the bad signature to the good signature, but it's too complicated. Yeah. Yeah. So there's OpenSSL libraries you can call to generate signatures and verify them and do the key stuff and have very little understanding of how they work. Yes? Okay. So last year we did a case study for a proof of concept for an animal testing company. And let's see, the animals are basically born and they're sold and sold and sold and, chopped up at the end.
Wow.
So,
What type of animals are we talking about?
Guinea pigs?
cows,
Oh, they really are chopped up.
yes. And they have RFID tags, and the RFID tags are stuck on the ear, and you can track them that way. So these are basically transactions between farmers, and the animals all have metadata, like their weight, veterinary care log, vaccines, and the permission to access the metadata depends on which organization you are, and we're storing that all in blockchain. I can't say more than that.
So who didn't trust whom?
The farmer over there doesn't trust the farmer over there. So here you have a replicated record in blockchain of the ownership.
And the farmers are comfortable with this?
We'll see. Just a proof of concept.
I really trust it.
And so now I'm going to talk about Bitcoin very briefly. So I would argue that Bitcoin is the inspiration for Hyperledger, because if you look back, one came right before the other. Even though they don't seem to have that much in common. Bitcoin was announced by this person or people, Satoshi, and basically solves the Byzantine generals problem, which is, you want to attack, and you send messengers back and forth discussing whether you should attack or not, and this is how you get them to agree on whether to attack or not, and then they all attack, with several generals being traitors. So this all Bitcoin actually relies on digital signatures of a slightly different elliptical curve, and proof of work, which I'll talk about. And Bitcoin keeps the ledger of transactions, which is basically I'm sending this number of Bitcoins from X to Y. That's all they have in the ledger. So that's one reason it's never been broken, because it's a very simple protocol, not like Ethereum. This is the announcement of Bitcoin. It was 2008. So, this the background for Bitcoin. There was a paper years and years ago on how to timestamp a digital document by Belcore. So they did stuff with the hashes of documents and the timestamps, and put some dependencies in them to make the timestamps verifiable. And hash cache was originally for spam prevention. So you could prove that you had done certain number of operations before sending email. It didn't take off, but it got used for Bitcoin. And I saw a reference to this guy, David Chaum. He apparently did a lot of work on, he could have come up with Bitcoin if only he published. But I don't have any of his papers because he didn't publish. Yeah. This is the Bitcoin core. So the transactions are broadcast to all peers, and the peers build up a block of prospective transactions, and the peers search for a hash of the block plus a nonce, where the hash is less than some value, and some value is adjusted every so often, so that it takes like 10 minutes on average to verify a new block on blockchain. And the winner broadcasts the block and the nonce, and after a while, it's considered confirmed. Yeah.
So why are you arguing that this is the inspiration for blockchain?
We talk later.
In a nutshell, you're arguing it's a digital signature plus the fact that, put another way, what's the equivalent of work that's being done?
That's one thing the Hyperledger has an advantage of. So the problem with Bitcoin is a limited transaction rate, because you can only execute one block of transactions every 10 minutes. So the throughput's pretty low. Also, it's burning the energy of Switzerland for calculating the hashes. Also, if there's a paper that says if you get 50% of the hashing capability, you'll break Bitcoin. So that's a disadvantage too. The advantages of Hyperledger, we don't do the hashing work, and the transaction rate can be whatever you want. Yes?
How much computing power would it take to break Bitcoin? Like, could Google do it with all of their systems?
Probably. Yeah, I don't know. It's basically using the marginal cost of electricity in countries that are not here for hashing. There's huge hash farms in Hong Kong and China and Venezuela. Yep. These are the top cryptocurrencies. So Bitcoin is number one, Ethereum is number two by a long distance. And these things, Bitcoin Cash is a variant of Bitcoin that tries to get around the throughput problem. Okay, so I've gone through all this stuff. So this is the Gartner hype cycle. So Bitcoin started here, went through here, and currently is in the trough of disillusionment. Soon to hopefully climbing the slope of enlightenment.
Should we invest now?
Sorry?
Should we invest now?
Yeah. This is also an old joke project outline. You start with the enthusiasm, disillusionment, and you proceed into panic, the search for the guilty, the punishment of the innocents, and praise and honors for non-participants.
This is true.
Yeah, and I'm making this up. Okay, and here's a bunch of references if you want to look at them. Most of them are Wikipedia, some of them are Bitcoin, and so forth. Okay, that's all I have.